Okay, what I'm going to attempt to explain in this video has to do with the fact that no matter where you measure the speed of light, it always comes up as a constant. Okay, and we've done everything. We tried to see the gravitational effects of the sun and how it would change the speed of light here on Earth. And every attempted measurement, speed of light becomes a constant. And so they say light travels on itself. I've made another video which we can go into. Basically, I believe the field that light travels on is gravity. I also believe all the other forces go on gravity. Let's first go into why I believe it's gravity. Gravity exhibits the same properties that would be required for a light to travel on. Light travels really, really fast. So whatever light travels on would have to be really, really hard. Whatever light travels on doesn't get in the way with movement. I can walk to any of these walls without any trouble. So it'd have to be really, really weak. And its velocity with respect to everything would have to be zero. Okay, well, first, I can walk to all these walls. So gravity is really, really weak. It doesn't stop me at all. Walk over here, but I can't jump to the ceiling. No chance. So gravity is really, really strong. So the next thing is, the velocity of gravity with respect to anything would have to be the same. And this is not as difficult as it sounds because everything makes gravity. We're going to go into the basic, and I'm going to be calling them for neutrinos, which is the basic element that creates gravity. We can get into arguments over, what comes out of an accelerator, the little pieces. I consider them to be fragmented charges. Whole nother video. Let's just stick and go with me with the neutrinos are creating the gravity. So we have like a neutrino here and a neutrino over here, and between them is going to be a gravitational field pulling them towards each other. The first thing we have to understand, and we're going to look at just a single line to start with, okay, is that this is going to have a direction in which it pulls. For example, over here it's going to pull this way more, and this will be stronger. If it's over here, this will pull this way more. So each one's mixing a field, and we're doing just the line between them. But they could also have a second component. Let's say that both these are moving this way. The field between them is also moving that way. So it has a direction to it of motion, but it's not along. It can be moving perpendicular to the lines of force. Now, if you go with conventional gravity, we have these two little guys here, and then way, way out here we have one little atom, and it's in the center of Alpha Centauri. And it's creating a line, and this line's going to come all the way to us, and no, that's silly. That's silly that something that far away is going to have a line of force that it's emitting, and it's ever so microscopic, but it gets here. No, that's not the way it's going to work, and I'll do it on a smaller scale to show you what I'm talking about. Let's say I add to this now. I'm going to put another one here, okay? This one cannot draw a line directly to that one. So this line of force goes into that one, and then it's re-emitted to make this line stronger coming out of here, okay? So the strength of this line from this one is dependent on both these. But the velocity, this component, is only dependent on these two. It's a readmission of this. So if this one's going this way, that would put this line rotating around here that way. That's not going to affect this line. Gravity is extremely localized when it comes to velocity. So basically, rather than the sun out here affecting this directly, the sun will affect the stuff between the sun, and then there's atmosphere in here, and it will affect the lines of force aren't direct. So the velocity of the gravitational field is really dependent on a very small number of neutrinos in the local area. This is what I mean by everything creates gravity. So gravity now becomes a very local event. Anytime you were to measure a distortion of gravity, which in this case would be light, a wave traveling down the gravitational field. Okay, and we'll get into another video to make fun of photons, but that's a different story entirely. Right now we're concerned with the velocity of light in any given experiment. You're never going to see the effect of the motion of the sun in a local gravitational environment. It's not going to affect it. The gravity comes through other neutrinos and has been re-emitted with a new velocity vector. That velocity vector is what determines how fast light travels. That means I could have light traveling this way and light traveling way out here that way. They're different velocities with respect to each other. But the velocity is constant with respect to the gravitational field lines that pass through that spot. That makes the gravity very local. Therefore, no matter how we're going to measure light, we're always going to get the same number. And we don't have to do any of that silly stuff where if I'm traveling this way close to the speed of light and somebody else is sitting still, their clock is faster, their clock is slower. Yes, but from the point of view on the spaceship, the other clock is still slower. It is still faster than their clock. Okay, when you start to get in that reciprocating time stuff, it really just becomes kind of what looks like made up. This solves that problem. Our limit of how fast any object, my little neutrino here going shooting that way, it is limited, and the equations of relativity apply to it within the local field. Okay, so we can have objects going faster than the speed of light with respect to each other, as long as they're in different isolated gravitational fields. Okay, and nowhere can they interact. The second thing which we have to take into consideration is gravitational fields are not instantaneous. E equals mc squared, E equals mc squared, basically is a result of the fact that gravity has a time constant. Gravitational change will ride on the gravitational field at the speed of light. So if this object goes from here to here, this object over here will only know that it's gone to here at the speed of light. It's not an instantaneous thing. Nothing happens instantaneously. Everything has a delay to it. So the old saying, if a planet appears out here, we know it now. No. We know it at the speed of light, the distance. We would then see the gravitational effect. This makes a lot of things easier. It allows us to use C for the other things which is used, like number one, E equals mc squared. Take a wire, run a wire from here, from New Jersey to California, and back, put 5 volts here. It shows up at the speed of light here. C, again the speed of light. Same thing, electrostatic. Because electricity is a distortion of gravity. There's one field, that's it. It responds at the speed of light. And therefore, all things that don't involve light, like electrostatic and mass, are still affected by this one constant. It's the constant that shows up everywhere. But always remember that when you're dealing with a gravitational field, you're dealing with it being localized by the surrounding material. Woohoo, phone ringing. Or is that what is that? That's not even a phone ring. That's like a balloon being let out. That's okay. I don't care. This is kind of funny. This is not the most professional video you guys have ever seen. And there'll be no special effects, just me drawing on a board. Either way, the localized effect, the fact that eventually you can get to a space that's velocity, not the strength, but the velocity of the field is determined only by what you would consider line of sight of that point in space. Got a point here, its gravitational field is the sum of all the lines in different directions and their velocities. We could have all kinds of different velocities. This one could be going that way, that one could be going that way, this one's coming this way. We sum them all together, but it's only things that are within that line of sight or that I can draw a direct line to. If I can't draw a direct line to it, I lose the velocity component of gravity. I still keep the strength because it goes in and it's re-emitted. But the velocity vector is dependent on the object that re-emits it. This is what gives us extremely localized gravity, and which allows the speed of light to be a constant, even though we have a giant sun moving around. That should affect it. It's not going to. It's way too local. So that's basically it. Thank you. Okay, this is getting kind of stuck in the middle of the other video, which I just did, but it's really along the same line. Back to our localized field. So here we have our Earth, and we have our atmosphere, and I'm going to be standing here, there I am, and my gravitational field and all my experiments are going to take place in basically a local gravitational field affected by this area, which is kind of small. But these are the only direct line of sight molecules that I can see, or that are within, that I can draw a line to without passing through another molecule. But this concept of local space varies depending on where you are. For example, if we have the sun way out here, the sun's velocity isn't going to be able to affect me because it has to pass through too many other molecules to get to me and will not affect the velocity vector of my local gravitational field. But if I'm out here in space, first off, we draw me blue because, well, I can't breathe, so I'm dead. And I've turned blue. But there's a lot less molecules around me. So to draw a circle that just includes the molecules that are directly in line with me, this circle could be big. It could be bigger than the Earth, depending on how far out I am, how far away, how many stray molecules are shooting through space, because there's no such thing as a pure vacuum. But the point is, this becomes the area that determines the velocity of gravity at this point in space. As where on the Earth, there's a lot of molecules around, so my relative gravitational field is smaller.